Analysis of a tall building with shear wall of RCC and steel plate. ABS retract tall structures are most influenced by lateral forces in seismic-prone areas. The most significant basis to be considered in the design of the tall structures is to oppose lateral forces which can cause instability and sudden failure of the structure. In this manner it is necessitated that structure ought to have enough lateral stability to oppose lateral forces and to control the lateral displacement of the building. The shear wall is one of the most generally utilized lateral loads opposing system in elevated structures. Shear wall has high in-plane stiffness and quality which can be utilized to all the while opposing enormous horizontal loads and support gravity loads. The incorporation of the shear wall has turned out to be inescapable in multi-storeys working to oppose lateral forces. It is exceptionally important to decide the successful, effective, and ideal location of the shear wall. In this paper, seismic analysis has been done on G+10 stories building in Zone 4. The analysis has been done considering shear wall of RCC and steel plate. Parameters like axial load, displacement, overturning moment, stiffness etc. are determined for different location of shear wall. Keywords: shear wall, seismic loading, lateral loading. 1. Introduction. The basic role of all kinds of structural systems utilized in a building-type structures is to support gravity loads. The most widely recognized loads resulting from the impact of gravity are dead load, live load, and snow load. Other than these vertical loads, buildings are likewise exposed to lateral loads brought about by the wind, impact load, or seismic tremors. Following are the various structural systems. 1. Structural frame systems. The structural system comprises of frames. Floor slabs, beams, and columns are the essential components of the structural system. Such frames can carry gravity loads while giving satisfactory stiffness. 2. Structural wall systems. In this kind of structures, all the vertical members are made of structural walls, generally called shear walls. 3. Shear wall, frame systems. Double systems. The system comprises of reinforced concrete frames interacting with reinforced concrete shear walls. Shear wall is a structural part in a reinforced concrete framed structure to oppose lateral forces, for example, wind forces. Shear walls are commonly utilized in tall structures subject to the lateral breeze and seismic forces. In reinforced concrete framed structures the impact of wind forces increase as the height of the structure increases. 1.1 Literature Review. Author. Name of journal. Title name. Research finding. Peter Timler et.al., 1998, 1. The Structural Design of Tall Buildings, 1998. Volume 7, pages 233 to 249. Experimental and Analytical Studies of Steel Plate Shear Walls as Applied to the Design of Tall Buildings. In this study, 3 variations of a steel-framed office building were used as case studies. Competitive reinforced concrete designs were also performed for economic comparisons. Astana ASL, 2001, 2. CA on Seminar, November 2001, San Francisco. Pages 1 to 18. Seismic behavior and design of steel shear walls. Seismic design of steel shear walls including provisions on how to establish strength of the wall as well as provisions on detailing to ensure sufficient ductility are made. Berke-Burek, 2013, 3. Journal of Structural Engineering 2013, Volume 139, pages 1928 to 1937. Effect of shear wall area to floor area ratio on the seismic behavior of reinforced concrete buildings. The results obtained from the nonlinear time history analyses including roof drift, inter-story drift, and the base shear responses are evaluated to obtain the effect of shear wall area to floor area ratio on the seismic performance of RC buildings that have no torsional irregularities. Sumit Pawar, 2014, 4. International Journal of Emerging Technology and Advanced Engineering, IJERT, 2014. Pages 244-252. Steel plate shear wall, a lateral load resisting system? Provision of part shear walls in Zone V is not enough to keep maximum displacements within permissible limits, whether it is a beam slab framed structure or framed structure with flat slabs with drop. R.Resmi and S. Yamini Roha, 2016, 6. International Journal of Applied Engineering Research, 2016, ISSN No. 0973-4562 Volume 11 Number 3, pages 369 to 370. A review on performance of shear wall. Shear wall provided along the periphery of the structure is found to be more effective. 1.2 Objectives of the present study. 1. To prepare 3D model of a tall building for detailed analysis. 2. To perform analysis of a tall building without shear wall. 3. To perform analysis of the tall building using RCC shear wall. 4. To perform analysis of the tall building using steel plate shear wall. 5. To compare the results of analysis of the tall building with and without shear walls. 6. To draw suitable conclusion from the above analysis. 1.3 Scope of study. The accuracy and the ability of the proposed structure are tested by static lateral load analysis in shear wall frame system. In order to check the validity of the proposed models are executed on taken into consideration structural systems, in which shear walls are modeled via wall factors of ATABS 2015. This analysis of lateral load resisting members in a building will assist us to increase the stability of structure against displacement and to decreases bending moment in vertical members, column. 2. Methodology. Design data of building. Dimension. Plan dimension. 25 m * 25 m. 25 m * 25 m. No of bay x direction. No of bay y direction. 5 bay. 5 bay. 5 bay. 5 bay. No of story. G+10. G+10. Typical story height. 3000 millimeters. 3000 millimeters. Bottom story height. 3000 millimeters. 3000 millimeters. Size of column. 800 * 800, auto selected. ISHB 400-2, auto selected. Size of beam. 200 * 600, auto selected. ISHB 400-2, auto selected. Thickness of slab. 200 millimeters. 200 millimeters. Thickness of shear wall. 200 millimeters, concrete shear wall. 200 millimeters, steel plate shear wall. Material. Concrete frame. Concrete. M30. Steel. HYSD 500. HYSD 500. Shear wall. M30. HYSD 500. 2.1 Steps for analysis and design of structural elements. 1. We choose Indian code for design. ATABS file new model use built-in setting with set, display unit, steel design code, concrete code section database. 2. Selection of grid plan. No of grid lines in X and Y direction are 5. Spacing in X and Y direction is 5 m. No. Of stories in building are 10. Height of typical story and bottom story is 3 m. 3. Selection of grid dimensions and defining the material properties of the building section. Define material properties. Add new material properties data. 4. Defining material properties and section properties of the building section. Define sectional properties. Section frame properties. Add new properties. Choose concrete frame section properties data. 5. Defining the slab properties of the building section. Define sectional properties. Slabs properties data. 6. Selection of beam and column section from toolbar. Draw the building frame section. Quick draw beam properties of beam section. Select beam properties. Draw the beam. Quick draw column properties of column section. Select column properties. Draw the column. Quick draw slab properties of slab. Select the slabs properties. Draw the slab. 7. Drawing the wall of the building. Quick draw wall properties of wall section. Select wall properties, draw the wall. 8. Designing the shear wall. Wall of the building assigned shell pier label, choose P1. Apply. Select wall of building assigned shell spandrel label, choose S1. Select wall of building assigned shell wall auto mesh option, shell assignment wall auto mesh option, advanced modify / auto mesh rectangular. Select wall of building assigning the load. 4. Analysis and results. Structural analysis is done for all the 8 models. Parameters obtained through analysis include maximum story deflection, maximum story drift, story shear, overturning moments generated while applying earthquake load on the structure. Results are shown below in tabular and graphical form. 4.1 Maximum story displacement. The values of maximum story displacement, as mentioned in IS 1893, Part 1 2002, for various models are given below. Table 3. Maximum story displacement, mm. Story. Model 1. Model 2. Model 3. Model 4. Model 5. Model 6. Model 7. Model 8. Story 10. 25.95. 25.816. 25.239. 21.24. 13.005. 9.959. 8.949. 7.738. Story 9. 24.827. 24.713. 24.155. 20.179. 11.68. 8.884. 7.938. 7.227. Story 8. 23.058. 22.966. 22.437. 18.682. 10.161. 7.7. 6.838. 6.484. Story 7. 20.773. 20.701. 20.213. 16.737. 8.566. 6.476. 5.715. 5.605. Story 6. 18.102. 18.05. 17.613. 14.407. 6.954. 5.243. 4.597. 4.667. Story 5. 15.162. 15.126. 14.75. 11.786. 5.367. 4.036. 3.516. 3.725. Story 4. 12.051. 12.029. 11.721. 8.98. 3.862. 2.897. 2.507. 2.819. Story 3. 8.852. 8.841. 8.606. 6.115. 2.496. 1.87. 1.608. 1.974. Story 2. 5.632. 5.63. 5.473. 3.373. 1.337. 1.007. 0.858. 1.202. Story 1. 2.577. 2.478. 2.399. 1.092. 0.468. 0.356. 0.301. 0.509. Base. 0. 0. 0, 0, 0, 0, 0, 0, 0, 10, 20, 30. Story 10. Story 9. Story 8. Story 7. Story 6. Story 5. Story 4. Story 3. Story 2. Story 1. Base. Displacement, mm. Story. Max story displacement. Model 1. Model 2. Model 3. Model 4. Model 5. Model 6. Model 7. Model 8. Figure 1. Maximum story displacement at different stories for various models. Comparing all the models, it has been found that the highest displacement value occurred at the 10th story in Model 1 and lowest value in Model 8. The value of displacement increases with height. There is abrupt reduction in the values of displacement, as shown in the Table 3 due to the replacement of concrete shear wall with the steel plate shear wall, SPSW. 4.2 Maximum story drift. The values of maximum story drift obtained for various models after analysis, as per IS 1893, Part 1 2002, are given in Table 5 and shown graphically in Figure 3. Figure 3. Maximum story drift at different stories for various models. The highest values of drift occurred at third story in Model 7 and the lowest value at the first story in Model 3. 4.3 Story shears. The values of maximum story shear obtained for various models, as per IS 1893, Part 1 2002, are given in Table 5 and shown graphically Figure 4. Figure 4. Story shear at different stories for various models. The highest value of story shear at the first story in Model 3 and the lowest value at the 10th story in Model 5. 4.4 Overturning moments. The values of maximum overturning moments obtained for various models, as per IS 1893, Part 1 2002, are given Table 6 and shown graphically Figure 5. Figure 5. Overturning moment at different stories for various models. Comparison of the models. The value of highest overturning moment is at the base in Model 3 while the lowest value at the base in Model 5. The value of maximum overturning moment decreases with increase in height. 4.5 Story stiffness. The values of maximum story stiffness obtained for various models, as per IS 1893, Part 1 2002, are given Table 7 and shown graphically Figure 6. Comparison of the models. The value of highest story stiffness is at the first story in Model 8 while the least value at the story first in Model 1. The value of maximum story stiffness decreases with increase in height. 5 Summary and conclusion. Total 8 models of the building were analyzed. Model 1 to Model 4 consisted of concrete frame while Model 5 to Model 8 were of steel frame. Model 1 of concrete frame and Model 5 of steel frame were provided with no shear wall. Models 2 to 4 of concrete frame were provided with shear walls on different locations. Shear walls were provided in the Models 6 to 8 of steel frame, on the same locations as for Models 2 to 4. The various concrete and steel frame Models 1 to 8 were analyzed and compared for various parameters through linear static analysis method considering seismic effect. It has been observed that the values of story displacement in concrete shear wall are more than steel plate shear walls, SPSW, while the values of story stiffness in steel plate shear wall are more than concrete shear wall. When compared all 8 models for the best location in the building, the steel plate shear wall, SPSW, provided at the middle, tubular form, and corner of the building has been found the best. It has been concluded that steel plate shear wall system is comparatively more suitable than concrete shear wall system in a building.